Okay, so next let's talk about matrices. So just a quick review of matrices. So a matrix is a rectangular array of numbers, and here they're going to refer to the elements like this. So they're going to use a capital letter for the elements. A little bit unusual, but that's what they're going to do. And we have I and J, which we stand for the rows and columns. And then we have the size of the matrix, and we denote it as m by n, where m is the number of rows and n is the number of columns. And we have an operation of adding two matrices, and so we take two matrices and we get a new matrix, and in order to add them together, they both have to be of the same size. And then to get the individual elements, which is what this stands for, the individual elements, you take the individual element of the first matrix and the corresponding same element of the second matrix and add them together to get the result. And you do that for each element in the C matrix. And then also we have a multiplication of matrices. It's not a scalar multiplication. We also have a scalar multiplication that we can define for matrices, but right now we're not talking about that. But we do have a matrix multiplication where you take two matrices and multiply them together, not a matrix times a scalar. So here we take A and B and we'll get a new matrix which we'll call C. And the size, now we know that if A is an m by n, then in order to multiply it by a b on the right-hand side, then b has to have n as the first dimension of its dimensions, or in other words, the number of rows here has to be n, and then p can be anything. And then we're allowed to multiply the a and the b. So the n here of a has to match the n here of b. And the resulting C matrix will then get its size from the m here of A and the p here of B. And to actually accomplish this multiplication, when we multiply A times B, we can ask, well, what are the elements of C? What do we actually have in C? We know what the dimensions of C have to be, but what are the individual elements? And again, here they're using capital letters to denote the elements. So if you want to know what the ijth element is, you do this. And what does that mean? We're going to take something from A and something from B, and we're going to multiply those. Those are two elements, one from A and one from B. And then we're going to get another element from A and B and multiply those, and we're going to keep doing that, and we're going to sum up the results. So which elements? So here we can see we're summing over k, so that is k becomes 1 and this k becomes 1. And then we take the I and the j. If we want to get the Cijth, we know what I will be and what j will be because we're talking about getting the Cijth element. So that's fixed. And then we put in k equals 1. This gives us a result. And then we put in k equals 2. That gives us a different result. This is, by the way, this is just a single element. In other words, this is just a scalar like a real number, and this is just a scalar like a real number. So just multiplying two scalars together here, and then we when we put in k equals 2, we're multiplying a different set of scalars, and then when we put in k equals 3, we're a different set of scalars, and we keep doing that all the way up to k equals n, where what is n again? N is this matching the number of columns in A and the number of rows in B. And so we just keep doing that all the way up to n. We'll get a string of things that we add up, and that will give us this. Now here's a picture I've never seen before, apparently from Wikipedia. So here's A and here's B. Remember that the number of columns of A has to match the number of rows of B, and number of columns is 2, number of rows is 2, so that works. And then the size of the resulting matrix will come from the number of rows of A, and that's here, and the number of columns of B, that's here. So that's a nice diagram. And then to know what this particular element will be in, this is C here. So to know what this particular element of C is, the diagram shows us that you take this yellow times this yellow to get this. And that's the dot product of this and this, although we haven't talked about dot product in this in here yet. And then to get this one, you take the dot product of this and this to get that. And that's exactly what this is. This is a dot product. For example, it could be the dot product of this and this to get this. That is, if this is, see, if this is what? This is a 1, 2. So if this is 1, 2, then to get the result, you take this dot this. Okay, the next thing they talk about is matrix vector multiplication. Well, we already defined matrix, so if we want to multiply a matrix times a vector, we can think of that vector as a matrix, and then we can do this matrix multiplication. So in other words, we're thinking of the vector as a matrix. So they say we may consider a vector x in Rn as a matrix of size n by 1. So if this is n by 1, then A has to be something by n. So they say it's m by n. And then we can do this multiplication, and the result will be an m by 1 result, or in other words, it'll be a vector with the number of rows of that vector as m, where m comes from the size of the number of rows in A. Okay, now they remind us that in the last section we saw that a linear map can be represented as a matrix, and vice versa. A matrix can be represented as a linear map. So what we're doing here again is doing a linear map on X. And we will see that when we construct neural networks, we take the weight matrix times a vector. So what does that tell us? That part of the process of the neural network is a linear map. Okay, next they just review the dot product. So we have two vectors, and we want to multiply them using this symbol, and we call that the dot product. And what it means is you take the first element of x times the first element of y, plus the second element of x times the second element of y, and you keep doing that, and then you add all of those up. So that's what's happening here. First element of x times first element of y, because that's I equals 1. Then put in I equals 2, you get second element of x, second element of y. Keep doing those multiplications. And then this says after you've finished going through all of them, writing them all down, put plus signs in between there and add them all up. And that's called the dot product. And we can also write this if we think of x as a matrix, then we could take its transpose, and we could write xt, x transpose y, or also y transpose x. Okay, now it's a little bit strange because they keep doing things backwards, because they mention the dot product. They don't define the dot product here. And so they define the dot product here, but they mention it earlier. Now same thing here. They use the transpose, but they define it afterwards, or they review the definition of it afterwards. But this is supposed to be a review, so I guess they assume that you've seen this before. So anyway, the transpose of the matrix A. So what does that mean? If A is an m by n, then it's like if you sort of flip the matrix, and you'll get, when you do that, an n by m matrix, and that's called the transpose. And what is this saying? this is saying, well, what are the elements of the transpose? Because here's the transpose, and what is this little ij doing there? That's saying, here we have the transpose, that's a matrix. And we're always allowed to put ij at the bottom to indicate that in this notation here, this is this book's notation, you're always allowed to put ij against the matrix, against any matrix, to talk about the elements of the matrix, the specific elements of the matrix. Well, AT is a matrix, so you can put ij next to it. So when you do that, you're asking what is the ijth element of this matrix, and the answer is, given here, it's the jith element of the original A matrix. So let's look at that. Here's A, B, C, D, E, F. When you take the transpose, you get this, A, B, C, D, E, F. So this row becomes this column, and so on. So they're asking, like, what is the, what is this here? How do we get this value here? It's B, but I mean, how can we explain that? Or how can we show that in notation? So we're asking, if this is the transpose, we're asking what? For the 2, 1 element, right? This is in the second row and first column. So we're asking, for example, what's the 2, 1 element of the transpose? And the answer is, it's not the 2, 1 element of this, but the 1, 2 element of this. So the 2, 1 element of this is the 1, 2 element of this. What is the 1, 2 element? 1, 2, it's B. So that's right. So the 2, 1 element of this is the 1, 2 element of this. That's what they're saying here. The ijth element of this is the jith element of this. So that's giving us kind of a roadmap about how to get the elements of this. You take the, if you want to get the ijth of this, you get the jith of this. Okay, next they talk about what is meant by a symmetric matrix, and that's where AT equals A. Well, if AT equals A, then A must be square, right? If it's not square, then AT is never going to be equal to A because it won't even have the same size. So at least a necessary condition is that it's of the same size, but that's not all we can say. That's not all that's meant by the fact that it's symmetric. So to be symmetric, a matrix has to be a square matrix, but then we can also say that its transpose is equal to A itself. So here is a symmetric matrix. What does it mean? It means that if you take the first row, then the transpose will have the same first row. So what does that mean? That means that when you put this down here, when you do this here, if you go down this way, you should have the same thing as when you go this way. And if you take this row, it should be the same as this. And when you have this, it should be the same as this. So basically, it's like you have a mirror image of what's happening up here over here. And they illustrate that here in Wikipedia like this. Like this element and this element are the same. 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 And so on. So again, this is the definition, but this is kind of the visual idea of it. Or you can also focus in on the individual elements. So we just said, for example, this element and this element are the same. So that means that if you take what is this element compared to this element? This would be Aij, for example. Then this would be Aji. So we can say that Aji is the same as Aij for every I and j. By the way, this Wikipedia uses a more standard notation for the individual elements. They don't use a capital A, Ji. They use a little a, Ji. So that's more standard than what we're looking at. That's more standard than using the capital A. to indicate the individual elements, but here he's using the capital A. Okay, so we have a square matrix, a symmetric matrix, and next we have a square matrix, and that's just a matrix where the number of rows equals the number of columns. So it's a square matrix. And then we have something called a diagonal matrix. So here's an example of a diagonal matrix from Wikipedia. You can see that everything is 0 except for along the diagonal. And then we have the identity matrix, which actually is a diagonal matrix, and it's the diagonal matrix with ones down the diagonal, all ones down the diagonal. And we know that when you take any matrix and you multiply it times the identity, you get the same original matrix back again. The identity matrix is the matrix which doesn't change the given matrix when you multiply the given matrix times the identity. Okay, the next topic is linear equations, determinants, and inverse matrices. Okay, so they say here we're taking a matrix and multiplying it times a vector. And we said that when we do that, we're going to get a new vector because this is like n by m, and this is n by m, so this is m by 1. So you're going to get n by 1 as a result. So you're going to get something which is m by 1 is a vector. So the result is going to be a vector because of the 1. So we'll call that vector b. But this is an equation, and so it's saying that what's here is equal to what's here. And so what's here is ax, and what's here is b. And when we say that they're equal, we mean, as we said earlier, when we say two matrices or two vectors are equal, that means that they're equal element by element. Now here, this is a vector, and this is a vector. So the first element on the left is equal to the first element on the right, and the second element on the left is equal to the second element on the right, and so on. Well, the first element on the right, the second element on the right, third element, those are here. And so, but this, when you multiply this out, as we said, we're going to get a vector, and the first element of this vector is going to look like this. So you can check that out for yourself, but it's true. So the first element of this vector should be equal to the first element of this vector, and that's what this says. This element is equal to the first element of b, and this will be equal to the second element of b, and so on. So this is the same as this. But this, of course, we can view as a system of equations, and these are linear equations because there's no square on x1, there's no square on x2, there's no square on x2 anywhere, and so on. So these are linear equations. So this is a system of linear equations. How many are there? Well, how many elements are there in B? Well, I think we said that B is going to be m by 1. So there must be m of these. So there's m equations. And then how many variables are there? That is going to come from the number of columns of A. Because we're going to take the first column of A times the we're going to take the first row of A times the first column of X. Well, there's only one column of X, but anyway, times the first column of X. So the number of columns of A and the number of rows of X, we already said they have to match, and that is going to be, as somewhere we said, n. So there's going to be n of these. So across here, there's going to be n terms. By the way, in math, we use the word terms when things are separated by a plus sign, and we use the word factors when things are separated by a multiplication sign. So I can say there are, what did I say? N terms here. And we already said there are m rows. So we have m equations, and each equation has on its left-hand side has n terms. So again, A is m by n, and that this m, if we have to go through this m is the number of rows of this system of linear equations, and this n is the number of terms on the left-hand side of each of these equations. Okay. Now the next thing here I think is not true actually. I haven't thought about it completely, but it looks like it's wrong to me. A necessary condition for such a set of equations to have a unique solution is that m equals n. So he says that m has to equal n, that is the number of terms here, and the number of equations have to be the same, but I don't think that's right. But anyway, I'm not going to go think about that too hard, but I'm pretty sure that's wrong. Anyway, let's just read what it says. A necessary condition for a set of equations to have a unique solution is that m equals n, i.e. it's a square matrix. So he's saying it has to be a square matrix. I don't think that's true. But anyway, let's just go on from there. Okay, so now he talks about the determinant, which he hasn't explained what it is yet. But I guess, again, we're assuming that this is a review. So in case the determinant of the matrix A, what matrix A? This matrix A, is not equal to 0, the matrix is called non-singular. And in that case, the inverse matrix, or A, has an inverse. Now again, he hasn't explained what the word inverse means yet. But again, I guess this is just supposed to be a review. So as a review, let's say that we know what determinant means, and if the determinant is not 0, then A has an inverse. And now, after that, he explains what he means by inverse. So what do we mean by the inverse? This is a symbol for the inverse. What do we mean by it, though? We mean the matrix here, that this is a matrix. It's a symbol for a specific matrix. And it's what matrix, what specific matrix is it? It's the matrix which, when we multiply times A, gives us I, gives us the identity element. And that's basically similar to what we mean in regular arithmetic when we have the inverse of 5. Oftentimes we'll say the inverse of 5 is 1/5. And what can we mean by that? We can say we can mean that 5 times 1/5 gives you 1. So 1 in that statement is the equivalent of I in this statement. And 1 is also called an identity element, and I is called an identity element. 1 is called the identity element for multiplication between numbers, and I is called the identity element for multiplication between matrices. Okay, anyway, so going back, this is what we mean by the inverse, that when you multiply it times A, you get I. Okay, so here he says, this is a little bit off also. Maybe this is because English is not this person's native language. I think that's a Dutch person. Anyway, they say a set of linear equations represented by ax equals b thus has a solution. But yes, he should be saying has a solution if the inverse exists. He didn't say that here. But anyway, a set of linear equations represented by ax equals b, thus has a solution if the inverse exists, or if the determinant is not 0. And the inverse, and the solution, sorry, will be A inverse B, because you can see that, going to here, if A has an inverse, then you can multiply the inverse, put it over here, and put it right here. So if you multiply, put the A inverse here times A, you just get the identity element. And then if you have the identity element, you multiply times x, you just get x. That's the point of the identity element. You just get x, and then we said we're going to multiply this side right here by A inverse, so that's what they have here. So if the inverse exists, or we can say if the determinant is not equal to 0 of A, then the solution, this has a solution, and the solution is given here, A inverse B. So this, you want the solution, it's A inverse B. So you might want to solve this, and you could do this, but he warns us or suggests that we don't do it that way. He says, please note that solving a set of linear equations by calculating the inverse matrix, which, basically, when we have this system of linear equations, we said that we can write it like this, and then we can get the solution to this like this, which basically means we've solved the system, right? Because if we know what the x vector is, that means we know what x makes this true. What x1, x2, x so on makes this true. So that's exactly what we're trying to find out when we solve a system of linear equations. We want to know what x's make it true. And here we have a formula for the x's. So we will have solved the system of linear equations, but he sort of warns us against doing that this way. He says, please note that solving a set of linear equations by calculating the inverse matrix is not a wise thing to do. Better ways to solve such systems are known and available in most linear algebra packages. So there are easier ways to do it, apparently. Okay, the next thing we go to is vector norms, inner products, and orthogonality. So the norm is basically just an extension of the idea of the absolute value, or like the size, right? The absolute value is kind of the size of something, and the norm is basically some way to talk about size of a vector. Of course, we can talk about the number of elements in the vector, but that's not what they mean by the norm. It's more to do with what are the values in there, and some way to sort of summarize those values. And the inner product will be used to help us get the norm, and it has other uses as well. And orthogonality just means when we have this notion, of course, of perpendicularity. The two lines are perpendicular, and it's kind of a generalization or extension of that idea for vectors, and particularly vectors, that are more than just 3 dimensions. We still have some way maybe to say that they're perpendicular even though we can't see them. So if we think of a vector like a 2D vector, we can think of it as an arrow, then obviously it has a length. And what is that length? Well, we talked about if we use the Euclidean definition for length, but that's not always the most appropriate way to measure the length, because if you're a taxi driver in a city like Manhattan, that length is sort of not that relevant. A more relevant length is the distance it takes you to get from one point to another. Usually you have to go sort of like on the sides of a triangle or something like that. So anyway, but if we use the regular idea of length, it's this idea. Now this assumes that the vector originates at the origin, but not, vectors don't necessarily originate at the origin, but this sort of works the same way. So anyway, this is the length, and we use the symbol for it. And if we had a vector, an arrow in three-dimensional space, we just have one more term here. We'd have x1 squared, x2 squared, x3 squared, and the square root of that. So you can see that we might generalize that. If we had a vector in R4, we could make it x1 squared, x2 squared, x3 squared, x4 squared, and we could do that for R5 and so on. And the inner product, which might be sometimes denoted with this symbol, is defined to be the norm of x, and remember that's going to give us a scalar, right? The norm gives you a scalar. This is all scalar stuff over here. And the norm of y is a scalar times the cosine of the angle between the two vectors. And by the way, here they're using this word, orthonormal basis. We've talked about the fact that basis vectors don't have to be perpendicular, but if they are perpendicular, they're called orthonormal. Actually, I believe orthonormal means that they're perpendicular and have unit length. So, two vectors don't have to each have unit length to be perpendicular, but we scale them down to unit length, and then we call them an orthonormal basis, or a set of orthonormal basis vectors. And here we've defined what we mean by the inner product. Now you might recall that we also say that the dot product is equal to this. And so if we have said in the past that the norm is equal to the square root of the dot product, and since this is another way to write the dot product, we can also say that it's the square root of the inner product. And this is not written too clearly. In the case of that the angle between two vectors should say two vectors x and y is 90 degrees. The vectors are orthogonal, and in that case the dot product is equal to 0, and that we can see that over here because this is the dot product we just said. And the cosine of, if they're perpendicular, the cosine of the angle between them is 0, so this will be 0. So that so xt, which is just like the dot product, is equal to 0. Okay, we have another definition, an orthogonal matrix. So what does that mean? Orthogonal matrix. Right? That doesn't seem to make any sense, right? Things are orthogonal if they're perpendicular. There's only one matrix here, so it sort of doesn't make sense to talk about an orthogonal matrix. You might be able to talk about something like orthogonal matrices, like two matrices are orthogonal, but that's not what they mean here, actually. So what do they mean by the word orthogonal matrix? So it's kind of a weird way to describe this particular matrix, but what it means is if the columns are orthogonal, or actually orthonormal. So anyway, let's just say if the columns are orthogonal, then it's called an orthogonal matrix, but we have to say a little bit more. If the columns are not only orthogonal, but they're all of unit length, and we know what we mean by length here. This is what we mean by length. So if you take a column and it's of unit length, and if each of those columns is orthogonal to each of the other ones, then that matrix is called orthogonal matrix. So maybe not the best name for this, because orthogonal matrix makes you think, oh, somehow it's perpendicular to something. But that's not what it means. It means that the columns are perpendicular to each other. Okay, but anyway, an orthogonal matrix, and we didn't talk about this, but an orthogonal matrix has an interesting property, and that is that it preserves the length or the norm of vectors. What does that mean? It means if you take a vector and you multiply it by an orthogonal matrix, you will of course get a new vector out. But one thing that will happen if the matrix is orthogonal is that the length of the output of this new vector, in other words, the length of that will be the same as the length of the original input vector. So in other words, here, okay, this is a mistake actually. This x and this x should not be the same. That's too bad. But I suppose what he meant to say is that ax, so you have, no, I'm sorry, it is true. So ax, that's the output, the length of that, the norm of that, is equal to the length of x. So by multiplying by a, the length of that is just the length of the original x. And then there's one more property about orthogonal matrices, and that is that the inverse and the transpose are equal. So that kind of makes life super nice. What do I mean by that? Well, oftentimes we would like to find the inverse of a matrix, but it's a lot of work to find the inverse of a matrix. Well, maybe it's not a lot of work if you ask the computer to do it, but it's a lot of work in general to do it. But here it says if you happen to have an orthogonal matrix, it's not a lot of work at all. All you have to do is basically flip the matrix, and that will give you the inverse. Okay, next we talk about eigenvectors and eigenvalues. And since this is a review, we'll just state it. That consider linear mapping. Okay, we know what linear mapping means. And basically a linear mapping means it's a function, but it also means that there's a matrix associated with this mapping. So there's some matrix associated with this linear mapping. Such a mapping can be represented with a square n by n matrix. In case for a specific vector x, we suppose that we have this here. That is, if you take a particular x for that matrix, we're given a matrix, if there's an x, which when you multiply a times that x, you just get a scalar multiple of x. So in other words, we know that when we multiply a matrix times x, it will give us a different vector, some other vector x, some other vector, and but if that other vector happens to be just a multiple of the original, then that's called, that x is called an eigenvector for the matrix A, and the scalar that it's a scalar multiple of is called the eigenvalue. So this lambda here is called the eigenvalue. Okay, so some interesting things now. If A is symmetric, when we talked about symmetric, it's just not, of course, not every vector, sorry, every matrix is symmetric, but if A is symmetric, then it can be shown that, we might say, well, how many different, okay, suppose we find an x, which has this property that when you multiply it times A, you get just a multiple of x. So that's called, we just said that's an eigenvector for A. But we might ask, well, how many other eigenvectors are there, not parallel to x, but in some other direction? Maybe there are other ones. So how many are there? So if A is symmetric, it can be shown that there are n eigenvectors and not only that, but they form an orthonormal basis of A. So let's say that again. If A is symmetric, then there are actually n eigenvectors for it. And not only that, but they form an orthonormal basis for A. So they form a basis, an orthonormal basis for A. Okay, and suppose that we take all of those eigenvectors and we make them, we take the normal ones, or the ones that are, that are of unit length, and we line them up vertically so that we can form a matrix. And let's call that matrix U. So U is just these, these are the columns of U. That's just these eigenvectors. Okay, so it turns out that that A then can be written as U times D. Okay, I forgot to say what D is. D is the we said that there are all these eigenvalues. For each eigenvector there's an eigenvalue, and we make another matrix, D we call it, which has these eigenvalues down the diagonal. So D is a diagonal matrix whose entries are the corresponding eigenvalues. Okay, so once again, we have this very interesting fact that A can be written as U. Remember, U is just these eigenvectors, basically, put in as the columns. So that's what U is. And then D, we just say what D is. We take the eigenvalues and we put them down the diagonal. And then U inverse, well, if we have U, we can get U inverse maybe. And so this is very interesting. Now we have that if A is symmetric, we can write it like this. Now who cares about that? Why is that interesting? Well, that's like saying who cares about, so this is called, we're factoring A into a product of three different vectors. I'm sorry, matrices, right? It's factoring because it's multiplication between, this is multiplication, this is multiplication. So why do we care about factoring? Well, let's just take the simplest case. Let's say we take the number 12. So we can factor it. Of course, we say we can factor it into like 6 times 2, or we can factor it into 3 times 4. So why do we care about that? Well, it certainly helps us, when we're doing algebra and things like that. It's useful. And the same thing with, we have, we have things like this. We have this expression here, and we can factor it like that. Or I don't know, we have this expression here, and we can factor it some other way. Or we have this expression. Well, why do we care about that? Well, it's obviously useful in various ways, in various calculations, and so on. So factoring is quite useful. And now we have this really interesting. This is like taking 12 and factoring it into the product of 2 times 2 times 3. Or anyway, it's factoring a matrix into 3 matrices. So this could be very powerful to be able to do that. It might be very useful when we're kind of doing algebra of matrices. So once again, let's just repeat it one more time. This is only talking about when A is symmetric. But we already reviewed the ideas of eigenvectors and eigenvalues. And we say that when A is symmetric, we can show that there are n eigenvectors that form an orthonormal basis of A. And then we can take those n eigenvectors and we can line them up like this. And we have to make sure that they're their unit size when we do this, unit length. And but we can just scale them to do that. So then we have this interesting vector U, which comes from A. And then it turns out that A can be factored in terms of that U and D is the eigenvalues which, along the diagonal, and then U inverse. So this is a very powerful or possibly powerful result. And the above equation is called the eigenvalue decomposition. So we're factoring or decomposing A into this. This is called the eigenvalue decomposition. I guess this contains the eigenvalues, the D. And next we're going to see some other kind of decomposition or some other kind of factoring. So being able to factor things is I guess I can say obviously important. And here we're able to factor A, and here we're going to have another way to factor under certain conditions. So these could be very useful. Okay, there's another way to factor matrix A. And this one is actually more general in the sense that it doesn't require A to be symmetric or even square. Remember, when we were talking about this type, we insisted that A has to be symmetric in order to do this. But this one says given any matrix A. So given any matrix A, we're going to be able to factor it into a couple different matrices. So what are these matrices? So we have something called D that's a little different than the other D, but sort of basically the same thing. And we have U, which is sort of the same thing. And we have V. Now remember, before we had U, D, and U inverse. So it doesn't look exactly the same. So the first thing they note is that actually, D is not going to be really the same. It's not going to be a diagonal matrix or truly a diagonal matrix, because if you look at the size of D, it's m by n. So what would it mean to be a diagonal matrix, right? You can't really have a diagonal matrix unless you have a square matrix. So it just means that the elements dii, so sort of down the diagonal, except the bottom part, it doesn't necessarily reach the bottom part. But anyway, the items that sort of dii that are along the sort of the diagonal, those are the only non-zero elements in the matrix D. Okay, but anyway, this is different, a little bit different than before. So remember that before U was a bunch of, well, it was the eigenvectors, but those were, we said, an orthonormal set, so they were all perpendicular. So now in the singular value one, it's also going to be an orthonormal set of vectors, but it's not going to be the eigenvalues, the eigenvectors of the original matrix A. So instead, they're the eigenvectors of A times A star. So what is A star? A star is basically just the transpose. Now, they get a little more particular here, and they say the conjugate transpose. So if you remember from, when you talk about the square root of -1 in high school or whatever math, you have two parts. So when we're talking about imaginary numbers or complex numbers, they have two parts. We have the something like 2i plus 3. So this is called the imaginary part, and this is called the real part. Actually, let me write it as 3 plus 2i, so just put the 3 first. So the conjugate of this, if you remember, is just 3 minus 2i. So 3 minus 2i is called the complex conjugate of 3 plus 2i. So that's all we mean by the complex conjugate. But also remember that if you just have the number 3, in other words, if you don't have an imaginary number, just a regular real number 3, and you ask what's the complex conjugate of that, it's the same. The complex conjugate is 3. The complex conjugate of 3 is 3. So here they're saying A star is the conjugate transpose. So it just means that if there are any complex numbers in A, then you have to take the conjugate of those. But generally, we won't have any complex numbers in our matrices, so we don't have to worry about that. But if you did, you just have to take their conjugate first and then take the transpose. But if all the numbers are just real numbers, then when you take the conjugate, you just get the same one. So then you just take the transpose of that. So that's what this is. So we can just think of it as the transpose. Now, if you remember, though, that A times its transpose, we mentioned this earlier, that is a symmetric matrix. So that's probably not that hard to show that, actually, because what do we mean by a symmetric matrix? Well, we know what we mean sort of in terms of, the mirror image, but we have another definition also, and that is that the matrix is equal to its transpose. So if I want to show that this is symmetric, I just have to use that idea, so it's probably not that hard. But anyway, we won't worry about it. We'll just accept that this is going to be symmetric. Okay, so what are we talking about again? So U consists of a set of orthonormal vectors, but where do these come from? So we know about orthonormal vectors from a symmetric matrix, but we're not saying. But we don't know that U is symmetric. In fact, generally speaking, U won't be symmetric. I'm sorry, not U, but A won't be. A is not symmetric, and so we can't do the same thing that we did earlier. But A times its transpose will be symmetric, so we can do the same thing as before and get the eigenvectors and form the matrix with those eigenvectors and call that U. And that's what this U is. So it's not the eigenvectors of A, it's the eigenvectors of A transpose, or A star. And that we can do. And then D is the eigenvalues for that. And then U is the eigenvectors of A star, that's here, and then this V is the eigenvectors of A star A. So it's not the same order, right? This is A star, this is A star A. So they probably have different eigenvectors. And so that's what V is. V is the eigenvector of A star A, and then we take the transpose. Okay, so that's a little bit, that's pretty complicated, but the point is, the main point is that we have a way to factor A. And before, it was a way only to factor A when it's symmetric, but this applies for every A. So that's kind of more powerful, more useful, or at least it could be more useful than the eigenvector or eigenvalue decomposition. So, so that's the point, that we can factor A, even if it's not symmetric, and this will be the factorization. And that can be pretty useful when we're playing around kind of with the algebra of matrices. Okay, next let's kind of scroll through this univariate function. So that just means functions of a single variable. So simple in terms of, well, we want to be able to work with functions of many variables. So it's simple in that sense. But anyway, let's just kind of scroll through there. So here's an example of a univariate function. Means just function of just uni means one, so it means of just one. Variate means variable, so it's just one variable, and we can do that in Python. We can define this in Python like that, and we can print it out. And so, Okay, here's another, this is still univariate. There's only one input, x, so that's univariate, and here they explain how to define this, I guess. It's not too hard, I suppose. And then we need to talk about derivatives. So we start out with derivatives of univariate functions. What do we mean by the derivative? And if you have to go back to your math class and recall this kind of definition, and we note that f is from r to r. It's univariate, in other words, and the derivative is another function, which will also be from r to r, and we know what we mean by derivative. It's sort of so if you have a function that looks like this, the blue curve, then the derivative tells you the slope. So, like, you want to know what's the slope right here. So, well, presumably it's like the slope of this orange line. So that's what we mean by derivative, slope. Slope of, like, this curved line. So, of course, at different places, it has different slopes. Okay, so most of the functions that we use are smooth functions, continuous functions like this, but not always. And we know, for example, the Rayleigh function doesn't look like that. Do they have a picture of it? No. But the Rayleigh function, it's flat, and then it goes up like that. So it's not, it has an edge. So, but that's not so typical. Anyway, this is another way to symbolize the derivative, this thing, or this thing, f prime, or this thing. So you can write it f prime, or you can write d, and you can put f here, and dx on the bottom like that. So these mean the same thing. This notation comes from Isaac Newton, and this notation comes from Leibniz. I forget what his first name is, but it comes from Leibniz. And both of these guys sort of discovered calculus at the same time without knowing that the other one had discovered calculus. So one was doing it in Germany, and one was doing it in England. This was about 1700 or something like that. And they both discovered it sort of simultaneously. So they developed their own notation, and so one person developed this notation, and one person developed this notation. And then we also have the concept of the second derivative, and that just means, if we take, it just means that you take the derivative of whatever you got when you took the derivative. You just do the derivative on. You take the derivative once, and then you can take that and do its derivative, and that's called the second derivative. And this is one notation, and this is another notation. This one's a little confusing. Why did they do it like that? But never mind that now. Let's just say this is the other notation. And then they say, there's all kinds of variations of these notations. You can write it this way. 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 You can write it. You can make up your own notation. But anyway, the idea is that it's the slope. And so here's some review of, if you have x to the n, this is the derivative. If you have the sine, it's the cosine, and so on. If you have just a constant, it's 0. Okay, then we also talk about some other thing in calculus called the integral. I don't think we're going to need this, but the integral, you have a function, and you're not interested in the slope of the function. That's the derivative. But suppose instead you want to know the area underneath the function between some two places that you specify. So you say, okay, here's let's say this is 1 and this is 10. I want to know the area underneath this, whatever curve this is. So that has a name. It's not called the derivative. So it's called the integral, and this is a symbol for that. And in terms of the notation, I'll just say it's not just a coincidence that this kind of looks like an S, in other words, for sum. It actually is kind of a sum. It's like you draw in these little rectangles in here, a bunch of little, and you sum up their areas, and that's an approximation to the actual area that you're looking for. Okay, the next section is on scaling and shifting functions. I don't think we're going to need this, but if you want to move a function up, so suppose you have a curve, like here's a curve function, and you want to get the same curve, but you want it to be higher. So what do you do? So suppose the first function is the sine function, and you want to push it up. So it's like the sine function, let's say here's the, says this is the x-axis right here. Sine function sort of goes through the x-axis. But suppose you want to push it way up to here, so it doesn't go through the x-axis, still has the same shape, but it doesn't go through the x-axis. What do? You just add a certain amount to the end. So you have like like 5 plus the sine of x. That's going to move it way up, so it won't go through the x-axis anymore. And in general, you just add some amount to a function to shift it up vertically. Okay, you can do these other things. I'm not going to talk about these. You can go through and check this out. So here, this is the idea. You have the original sine function. You can push it up to the black one, or you can move it to the right. So you have the original gray one. You can move it to the right. How do you do that? They tell you up there. You can move it to the left. You can, I'm sorry, that's not moving it to the left. You can sort of stretch it up and down. How do you do that? They tell you up above. And what is this? I don't know what this is, but this is some other change. Okay, we're not going to go through this. This is calculus. Not going to do it. More. Okay, now we're talking about a function of two input variables. So we'll have a different kind of graph for that, and so on, and so on. So when we talk about derivatives for what we call multivariate functions, where we have more than one input, we use this symbol, a little different than the D, just so it helps us remember that we're not talking about just a univariate function. We just use another symbol to help us remember that. And can sort of use the same kind of idea. We can take the derivative with respect to one, and then the derivative with respect to the other. Okay, let's just keep going. Okay, so now we get to the important part, and this is the chain rule. So let's say here we have three functions, f, g, and h. So first of all, what does this mean? This just means e to the minus x. So why do they do it this way? Because it's easier to type it. So if you have to put a superscript, that's more work when you're typing. That's why they do it this way. You can just type exp bracket minus x close bracket. You don't have to do some superscript. So that's why they do it this way. But it's the same thing. It's e to the minus x. Okay, so we have three functions, x squared, e to the minus x, and cx. So we can do what we call function composition. And it's written like this, h of g of f. So what it means is you start with f and you put it into g. So that means what? Well, g, what does g do? It takes whatever x is and puts it in the exponent for e. But now, instead of putting in g of x, which is what we have here, we're putting in g of that. So it's e to the f. But what is f? F is x squared, so it's e to the x squared. Okay, and then we take that and we put it into this function. So that just multiplies whatever we put into it by c. So we get c e to the minus x squared. Okay. So now we can find the derivative of this composition. That is, we call it k, and we can find the derivative of k. Why not? We can find the derivative of this thing. Why not? Well, maybe. Maybe we can. Maybe we can't. But we can try. Maybe you don't know how to do this. But in calculus, we're sort of taught how to do that. So we could do it. We could find the derivative of that. And that's what this is asking for. And we did it. They did it here. But the chain rule kind of gives you a step-by-step way of getting this. So that's why we want the chain rule. When we have a composition of functions, if we want a step-by-step path for finding the derivative of that composition, that's what the chain rule tells us how to do. So here's the same picture again. Here we have this, which we can look like that, visualize it like this. First we put x into f. So first we put x into f. Then we take that and we put that into g. And then we take what we get out of that into h. And then we get the answer out as y. And here's the chain rule. But this is just for when we have 2, not 3. We're doing 3 here. And it's a little strange to have started with 3. But anyway, they did that. But just for 2 functions, a composition of 2 functions, g and f. So the chain rule tells us what the derivative will be. So they go through sort of some, I don't know what they're doing, but here's the answer. G prime f of x times f prime of x. Okay, well, hopefully you learned this in school, so we don't have to go through all of this. And here's when we have 3, you can also figure out the chain rule. So it looks like this now. Now, if we go back and use the other notation, not the Newton notation, which was when we put the prime there, but we use the Leibniz notation, then this looks like this, using Leibniz notation. The same thing, using the Leibniz notation. And here, the notation is very suggestive, because it says we want dy dx. See, y is the output, and we want the derivative of y with respect to x, which you can think of as what happens when you change x by a little bit. How does y change? That's what the derivative is asking. So, of course, when you change x, it's going to change y because it's going to change f, that's going to change g, that's going to change h, which is y. So, yeah, it is going to change, but we want to know how much it changes. And that's what this is asking. And the answer turns out to be this. And this is, the notation is suggestive because it looks like what? This is canceling with that, and this is canceling with that, and you get dy dx. And that isn't really allowed, but maybe that's kind of the genius of Leibniz's notation, that it kind of suggests, just from the notation, that this is the correct formula. But it's not quite as simple as just canceling. Can't really cancel. This is not really like a floating dy, this is not like a floating dv that can be canceled with this floating dv. These are connected. These are like this, just part of one notation. So not like you can just like treat this as a single thing and this is another thing. Not really variables like that, or even separate items. But anyway, this is what we want, this formula. So we're going to use this. We're going to rely on this kind of calculation. So once again, what does it mean? It means when you jiggle x, when you change x by a little bit, how much does y change? That's what this notation means. And the answer is you can divide it into 3 of these. This says when you change y, how much does, I'm sorry, when you change v, how much does y change? And when you change, let's do it this way, let's start from this one. When you change x, u changes, and then when you change u, v changes, and when you change v, y changes. Okay, but if you'll notice, this was only one input variable. This was back to the univariate case. Kind of looks like maybe it's not, but no, the only variable is x. So what if we want to go to the more complicated case of 2 input variables, or 3 or 4 or 5 or 10? Then what do we have to do? Well, in here they're going through, like, I guess a kind of a proof or something about how it works, but let's just skip to the answer. And let's skip to this form of the answer instead of this form, or whatever form they had. Yeah, anyway, let's skip to this form. Well, what's the answer here? The question is, when x changes, how does f change?